Hi there, thanks for joining us. Andrew Dunkley here, the host of Space Nuts, and we've got a jam-packed episode coming up for you. Today, we're going to be looking at the rivers of Mars, some new information that could lead to cementing the potential for life on the red planet. Maybe, could be, might not, don't know. And the age of the universe, new speculation that it might be twice as old as we think it is, just like Fred. And that's just part of it. We're also going to be answering audience questions. One is titled Fred's Conjecture, which we're going to talk about. I won't reveal any more at this stage. Somebody's asking about Fred's musical history and the thickness of the galaxy. Yes, it is pretty dumb. We'll talk about all of that today on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here he is, the man of the moment, Professor Fred Watson, astronomer at large. Hi, Fred.
And indeed, twice as old as everybody thinks the universe is.
Yes.
Yes, thank you, Andrew. Good to see you.
You too.
An unusual time of day and week.
Yes. Yes, we're doing this on a Sunday because the stars wouldn't align for us during the week.
That's right, but never mind. That's all right.
We circumvented them instead.
I think you're on fire on a Sunday morning, Andrew. Two dad jokes. Well, gosh.
Oh, dear. Yes. Now, we've got a lot to talk about, so we might just get stuck straight into it. And this first story indeed intrigues me, and that is about the rivers of Mars. And they've released some new information. I think they've used computer modelling to figure this out, which is not uncommon these days. But they do reckon that the rivers did run for quite some time without paddle steamers, but they were running rivers on Mars, and the major point here is long enough to perhaps have seen the early development of life.
Yeah, that's right. It's a really intriguing story, this, and its consequences actually go beyond the planet Mars. There are 3 places in the solar system where we believe there have been or are rivers. One is a place called Earth.
Yep.
The other is now Mars. Do you know what the third one is then?
Earth?
Mars.
Earth, Mars, and Titan.
Titan, that's right. Titan.
Where they're still running. They're still running. They've still got rivers.
Titan has rivers of methane and ethane. That's those hydrocarbon liquids.
That'd be a fun swim.
Yeah, minus 195 or whatever it is. I think it's about that. Yeah, well, it's a place that people are going to visit with a spacecraft whose name I've forgotten. It's Dragonfly. That's it.
That's the one.
Spacecraft which is going to go and fly around on Titan and look at the rivers. That's not quite part of this story, but the reason why this story is a story and not just a bit of fiction is that the modelling, exactly as you've said, and this comes from MIT, the Massachusetts Institute of Technology, geologists who've worked there. They've done computer modelling, comparing with what we know from imagery, either satellite imagery looking down on a surface, as with Mars and Titan, or what we know about the Earth's rivers. They've modelled the way liquids and the sediment that they carry, how they move across the surface of worlds like Mars, the Earth, Titan, knowing about the gravitational pull of those different worlds, because all 3 of them are all different, and have made these calculations that suggest that some of these rivers were very long-lived. So sort of homing in on Mars, there is some surface area, the surface of Mars we know has had liquids there because we see all the evidence of meandering channels. We see beaches, actually, remnant beaches from perhaps oceans. But what we don't know is how long the water lasted. And these river valleys, were they formed over a matter of maybe a few thousand years or something like that? Or were they formed over much longer periods of geological time, which would suggest that maybe the water was running for longer, and there was a greater chance of life kicking off. And in particular, I remember there was a story it's probably a month or so ago that we didn't cover, which just hinted at this work. And what was shown, and there's a lovely image of this on the space.com website as well, is a region of Mars. It's got a lovely name. It's called Scrinkle Haven. Scrinkle Haven is a region of Mars where there are bands of rock, basically, that form lines on the surface, sinuously curved lines. And the suggestion is that those rock bands were laid down by sediments from a flowing river. And of course, that philosophy is one reason why the Perseverance rover is sitting where it is at Jezero Crater, because Jezero Crater has a river delta in it, a place where a river has dropped sediments on the floor of the crater when there was a lake there.
Which is very, very common on Earth. We see a lot of river deltas.
Exactly right. And the thing about a river delta is it carries the sediment from basically all the way along the river valley. And so the thinking there is that if you're going to find any evidence of living organisms that existed in that river,
that's where to look.
That's where to look, because that's where it would have been dumped. So these scientists have essentially they've applied their modelling technique to calculate, particularly homing in on Mars, to calculate just how fast and how deep the rivers might have been. They have looked at Gale Crater, which is a place very familiar to Mars watchers, because that's where the Curiosity rover is. Perseverance is at Jezero, Curiosity is at Gale Crater, named, by the way, after an Australian amateur astronomer of the 19th and early 20th century. So Gale Crater is a place where they've looked at as I said, how fast and deep the rivers were, and they think they flowed for at least 100,000 years at Gale Crater. But at Jezero, at least 1 million years, 10 times as much. And that's what they're suggesting. This study team is suggesting that is long enough for life processes to evolve. So that's the main conclusion of what we're talking about today, Andrew. But they've, as we've hinted already, they've been able to test this with other examples. So they've basically applied the same algorithms to Titan, and worked out whether how long these rivers might last, and look at maybe the length of time that we might see actively flowing rivers of methane and ethane on Titan. I mean, it would be terrible if they worked out that it was going to dry up before the Dragonfly spacecraft actually got there, but that doesn't seem to be the case.
Not likely.
No, that's right. So we've got lovely images of those rivers. Nowhere near as deep knowledge of Titan's rivers as we have of Mars's rivers. But the Cassini spacecraft, which you and I raved about for about a decade, sending back marvelous infrared, actually radar images, if I remember rightly, of the surface of Titan, because radar can penetrate its thick, opaque atmosphere, and revealing these river valleys, lots of tributaries, all the sort of stuff that you would expect. So one thing that they have noted, though, is that unlike Mars, which does show deltas, like the one in Jezero Crater where Perseverance is sitting, you don't get these deltas on Titan. And so they are suggesting that means that those rivers, the hydrocarbon rivers, don't flow fast enough to carry much sediment. And remember, the sediment on Titan is actually frozen water. It's water ice, because that's what the bedrock is.
Yes, it is too.
It's not rock, it's water. But that they would have included this in their calculations. And so what they've suggested is that that these hydrocarbon rivers don't flow fast enough. But they've looked at the river width, depth, slope, flow rate, all of that stuff to calculate these things. And I think they've explained that. I think that is the conclusion they've come to. Yes, okay, that's fair enough. The rivers are not flowing fast enough, whereas they did on Mars.
Yes. So the rivers on Mars are more like the rivers we have on Earth.
Yes, indeed. And
what about in terms of length and depth?
I
Would
think
they have been similar?
Yeah, I think so. Given that Mars is a smaller world, it's half the diameter of Earth, although it's got roughly the same land area as the Earth has. It's also, of course, only got a third of Earth's gravity. So all of that will probably, I suspect, feed into how long a river could be on Mars, and it may actually mean that they wouldn't be as long. But just to give them some confidence in the work that these, the results that these algorithms develop, this MIT team have actually tested 500 rivers on Earth to make sure that they get the right answers. Because on Earth, we know what the right answers are. We see the deltas, and we know about the amount of sediment being carried. And apparently, the predictions are pretty good. They've verified their accuracy on the planet Earth.
I suppose from reading the information, the thing that I scratch my head about is the rivers on Mars seem to have been fairly short-lived when you talk about the age of a planet and its evolution. Is 100,000 years long enough for life to start to take hold? Is that a reasonable assumption?
I had exactly the same thought, Andrew. And I'm not enough of an evolutionary biologist to know. But it may be, if you've got the right materials, the process of life kicking off doesn't take very long. It's sustaining it that, I guess, is the critical thing. And if these rivers flow for, 100,000 years, they're suggesting 1 million years for Jezero Crater.
Yeah.
In fact, and I should say these are lower limits, so it's at least 1 million years. So yes, maybe by the time you get to 1 million years, you've got some resilience in any kind of any early forms of life that you've got in your river or its surroundings.
Yeah,
but it's a good question. As I said, the same thing occurred to me. I should talk to some evolutionary biologists and find out what they think would be the length of time it would take for life to kick off.
Yeah. Well, as I've said in the past, my theory is that the entire universe has the seeds of life. It's just a matter of getting the chemistry right, and it'll pop up. That's my theory. I know it's they've found that in studying materials from asteroids, etc., that is actually the case in many respects. Yeah. They've found the basics, but it stands to reason that if you get the right stuff in the right combinations in the right place at the right time, you're going to pop up a few weeds.
And look, I think you're right, Andrew, as well. I think your analysis is correct. Water is the most common two-element molecule in the universe.
So how does that then translate to the potential for life on, say, Titan, which is a very different environment and very, hostile as far as we are concerned? But you've got ethane and methane flowing through water ice.
Yeah, that's right. You've got all rich in hydrocarbons, complex organic molecules, rich in water. Could be a no-brainer, really.
Yeah. Well, there you go.
I guess the conventional wisdom might be, minus 190. I think that's about the temperature on Titan. Far too cold for biological processes to take place, but that ain't necessarily the case. If you've got biology that relies on things that, for its working fluids, and the working fluid would be the liquid hydrocarbons, then if that biology can exist, it might well find minus 190 degrees Celsius a very balmy temperature. I do remember in the early days of Cassini, there was some work that suggested that there could be biota, in other words, living organisms, which use the ethane and methane as their working fluid, and they would breathe hydrogen and would eat, acetylene. That was the molecule that they said they would would eat. And tantalizingly, I don't know whether this was borne out over over later studies. This came from the very early days of Titan. Remember the Huygens probe that landed on Titan? The very early days of Cassini, I beg your pardon, with that Huygens probe that landed on Titan. They found that the acetylene and hydrogen were depleted near the surface of some of these lakes, and were suggesting that maybe that demonstrates that there are some acetylene-eating microbes actually living in the body of those lakes. What about that for intriguing?
I know. You could sell a lot of Tums on a planet like that. Settle the stomach down. Good grief.
Yeah, it certainly would, yeah.
Yeah.
At minus 190, I think you would.
Yeah, for sure. All right. It's a fascinating theory, and if you'd like to chase it up, you can read all about it in the journal Proceedings of the National Academy of Sciences. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our next topic is just as intriguing because it's thrown a real spanner into the works. Now, we have talked about many times evidence that proves that the age of the universe is 13.8 billion years, give or take, 13.787, let's be exact. But now there is, I won't say evidence, but a new pitch being put up that it's probably a lot older. In fact, almost double, Fred. That's way out there when you take into account what is commonly understood and believed at this point in time.
Yeah, I mean, if it was you or I proposing that, people would fall about laughing. But this is the paper that's come from a researcher at the University of Ottawa in Canada. It has survived peer review. It's appearing in that eminent journal, the Monthly Notices of the Royal Astronomical Society, in a paper entitled JWST Early Universe Observations and Lambda CDM Cosmology. And translating that, it means the James Webb Space Telescope has observed galaxies which we are seeing when the universe, according to the current model, was only 300 million years old. Long enough for rivers on Mars, although there weren't any planets at that time, 300 million years old. And that's in tension with our models of the universe, which suggests that galaxies take longer to evolve to the level that they are at over the history of the universe. So what it's saying is the observation of these early of these galaxies when the universe was at an age of 300 million years old shows galaxies that we think must have taken longer to evolve. That's the tension. And indeed, I think it was last week, and we've certainly had it before, some of our listeners have raised that issue and said, what do you think about that? And so this is not my answer to that, as normally you get. This is Dr. Gupta's answer. Dr. Gupta is a scientist, as I said, at the University of Ottawa, Rajendra Gupta. And so the theory that has been proposed by Dr. Gupta is that there is a new model that we need to build to give us a better idea of the age of the universe, and that is what has been done. And that new model suggests that the age of the universe, as you said, rather than being 30.797 billion years, is actually 26.7 billion years.
That's a big jump.
Yeah, it's not just a tweak, is it, really?
Sure.
We've seen it go from 13.6 to 13.7 before, but not doubling in size. So it's an attempt to resolve to resolve that tension between the observations that we see and our traditional interpretation of the evidence for the Big Bang and the age of the universe. Sorry, I thought you were about to jump in there.
No.
Okay.
I was gasping with horror.
Okay. Yeah, okay. So was I. What this model takes is something that was actually proposed decades ago, in fact, by Fritz Zwicky, who was an astronomer who's he's actually the first person to postulate dark matter, because he measured the what we call the velocity dispersion of galaxies in their clusters. In other words, the amount of speed that they have as they circulate around the center of gravity of a cluster. And he worked out that there wasn't enough material to hold the galaxies in. And so that was a puzzle that remains today. He highlighted that, and most people just said, well, we can't understand that, so we'll ignore it. And it was really ignored from the 1930s when he made that observation until the 1970s, when people like Ken Freeman here in Australia and Vera Rubin in the United States said, we've really got a problem because galaxies are rotating too fast to hold themselves together.
Yeah.
So all of that. So Zwicky had a theory it's called the tired light theory. And in fact, I remember some of my colleagues at the Royal Observatory, Edinburgh, back in the 1970s and 80s, late 1970s, postulating that tired light might be a better answer to our understanding of the expansion of the universe than conventional redshift. So the tired light theory, the original tired lights theory, said the universe isn't expanding. What you've got is photons losing energy and hence being redshifted just because they're getting tired over time as they reach our planet. So that was the basics of the tired light theory. But it was kind of knocked on the head by things like the discovery of the cosmic microwave background radiation, which lets you see the flash of the Big Bang. That's what squashed the steady state theory of the universe, which I suppose tired light is a version of. So we've kind of discarded all these ideas because of the success of the conventional Big Bang theory, with all the tweaks applied, which include dark matter and the dark energy that we've known about since 1998. You throw all those into the mix and you get a good solid value of 13 point whatever it was, 13.797 billion years for the age of the universe. So what Dr. Gupta, actually it's Professor Gupta, I beg your pardon, has proposed is that the tired light theory didn't work. He's saying, Dr. Gupta is saying that the redshift theory doesn't work either. But if you combine the redshift due to an expanding universe doesn't work either.
Yeah.
But if you combine the two, you get something that works. That's the bottom line in a nutshell. I do have the abstract of the paper here, which basically says that the James Webb Space Telescope findings are in strong tension with the conventional cosmological model, what we call the lambda CDM model. Lambda is the cosmological constant, which is what's causing what's resulting from dark energy, we think. CDM stands for cold dark matter. And the abstract goes on to say, while tired light models have been shown to comply with the James Webb Space Telescope angular galaxy size data, they cannot satisfactorily explain the cosmic microwave background radiation and various other things that our current theory explains. So the group that's working on this, Professor Gupta's group, has developed hybrid models that include the tired light concept in the expanding universe. And that is basically the bottom line.
Okay.
And so it goes from there through various metrics and Einstein and Friedman equations and a whole lot of gobbledygook to come out with an age of the universe of 26.7 billion years.
Okay. Fred, how do you feel about that?
I feel that at the moment, that is something that's coming from left field. I love things that come in from left field, as you do too, because they might turn out to be right. So what we're going to have to see is how the astronomical community, and in particular the cosmologists, react to that. over the next few years, because this paper in Monthly Notices will definitely provoke a flood of answers. It's unlikely that it'll provoke an immediate response saying, "Oh yeah, you're right. Yeah."
That doesn't happen often.
Doesn't happen, no. But because the basic paradigm is the universe is that age, and it's still, I mean, it goes back. It hints to the reason why the Big Bang theory was unpopular back in the late 50s, early 60s, when it was a new theory. And the reason for that was that if you used the then known characteristics of the expanding universe, you wound up with a universe that was too young for, it's younger than the planets that are in it, because we can measure the ages of planets geologically. And so it's really interesting that we might be seeing a similar shift in the paradigm, the basic paradigm. That was fixed back in the 50s and 60s, 1960, whatever it was it 67 when the cosmic microwave background was first observed, and that really was the death knell for the steady state theory. And the Big Bang theory had to be patched up so that you do have a universe that's old enough to have stuff in it that we know, whose age we know.
We always thought that the James Webb Space Telescope would make observations that would challenge current theories, and maybe it's already happening. And this is a classic. This is not just a classic example. This is an absolute flip the lid type of theory. But they're basing it on James Webb Space Telescope observations, suggesting that there are galaxies out there that don't fit in with the current age of the universe. And why is that happening? And they've based this new theory on some of those observations, I think.
Yeah, of course, that's right. That's really the bedrock of this idea that because there is this tension between the size of those galaxies. They look smaller than they're supposed to, and so I guess what the suggestion is here is that they're further away than we thought they were, because we're looking back a lot further in time than scientists have thought. So what a shift. I mean, if you and I are talking in, say, 2 years, 3 years, maybe, about, I hope we still are.
I do too.
A universe that's 26.7 or 27.6 or whatever it is billion years old, then you'll know that that things have shifted, that the idea has shifted. So it's a real milestone. It's something to look forward to and see what happens.
I'm certain it will also spawn a lot of theory and questions from the Space Nuts audience, because when we get into these realms of, well, what we absolutely believe may not actually be right, it just opens the floodgates.
Yeah. Great stuff.
I think we're going to be talking about this a lot more, and I'll be really interested to see how people in the astronomy and space science world respond to this. I think it's a can of worms. Is what I'm trying to say.
The word you're looking for is the Naziverse.
Yes, probably so. I think this is just the beginning of some pretty decent debate on the age of the universe, indeed. And if you'd like to read into that more deeply, as Fred said, it's in the monthly notices of the Royal Astronomical Society. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying was a go.
Space Nuts.
Right, let's get into some questions, Fred. And I've got one audio question, and we've got a couple of text questions because we've been getting a few in, so we'll deal with those. This one comes from Clive. Clive's been in touch with us before, but we've got him thinking.
Hi, friend Andrew. It's Clive from Worcestershire, England. Thanks for a great podcast. You guys are wonderful. I loved the one about follow-ons podcast. That is just awesome. And thanks so much for the follow-on. I think Fred might be being a bit modest. He was talking about dark matter falling into black holes, or he edged towards that. And I can't find much about that anywhere on the internet. So I'm going to call it Fred's conjecture. I think it's a really interesting thing. It's our favourite subject, all of us, because it's got dark matter and black holes all in one. And I was going to just congratulate you on the great episode with the follow-ons, but it struck me, there's got to be one more question. It is interesting, if dark matter is falling into black holes, presumably it doesn't produce anything in the way of radiation, because I'm guessing the radiation when matter falls into black holes is like Bremsstrahlung. It's got to be charged particles falling in. I wonder if I'm right in that. So would it be possible to spot the different signatures of ordinary matter falling into black holes and dark matter falling into black holes? Because that's a really interesting thought. I'd love.
Oh, yeah, he got cut off, but I thought it was worth running because he's asked
great stuff.
He's asked a pretty deep question there, and thanks, Clive. And sorry you got cut off, but I think we got the gist of it. We did talk about this not so long ago, and Fred's conjecture. I thought that was a nice touch as well. But what do you think of Clive's thoughts?
I love them, but there's a couple of things I might just point out. So normal matter, when it falls into the black hole, doesn't radiate. So Clive mentioned Bremsstrahlung, good German word for things like Cherenkov radiation that's emitted when things exceed certain speeds. But I think dark matter, as it disappears into the black hole, is not the source of the radiation that we get from black holes. That comes from basically frictional heating, I think, just by the fact that these the debris surrounding a black hole, and it's got to be a black hole that's gobbling stuff up for it to be visible at all. It's that stuff is accelerated to such high velocities, high energies, that you've got extraordinary heating that produces X-rays and things of that sort. But it ties in also with the magnetic field of the black hole. So there is this sort of radiative, the kind of physical processes that Clive was talking about does come into being when you've got something moving through a strong magnetic field. So I don't think there would necessarily be a different signature. There might be. I mean, we do conjecture with some models of dark matter, and everything we know about dark matter is really a model because we've got no evidence as to what it actually is. Except we know it doesn't interact in any way with normal matter other than through gravity. So but some of the models for dark matter suggest that dark matter particles, if you've got such things as dark matter particles and dark matter antiparticles, and they collide and annihilate, you'll get a certain gamma ray signal, which would have a specific characteristic. And that's the sort of thing that people are looking for. They've looked for signs of that particular frequency near the centers of galaxies, where you might expect the density of dark matter particles to be higher, and so you'd expect collisions to be more frequent. But so far, nothing significant has yet been found, as far as I know. So some really interesting ideas there from Clive. I should look a little bit more closely at that, though, to see, because it's an interesting thought that would dark matter falling into a black hole have a different signature in the radiation?
Yeah, I thought that was brilliant.
Yeah.
And I guess we'd have to, and as he said, he's been searching the internet to try and find out. Well, the internet's a black hole unto itself, which is probably why I can't find anything. But it's probably such a new concept, new theory and how do you test it?
You ask Fred. That's the way to do it.
That's So what's the answer?
Maybe.
There you go. So once again, we adequately answer your question, Clive.
That's the same answer to is the universe 27.6 billion years
Maybe.
old?
It's a great answer.
I think it's the answer to everything in astronomy, isn't it?
Pretty close.
You're always. No, we do think we do have some certainty about some things.
Yes, yes. But then the James Webb Space Telescope takes a picture and says, well,
Actually,
sorry, but you mere humans are wrong.
yeah, think again, lads and lasses.
Yeah, yeah. All right. Thank you, Clive. Lovely to hear from you. Andre from the Netherlands has written into us. Hello, Space Nuts. I have a few questions for your show, which have been bothering me for a while. First, our Milky Way has a diameter of about 150,000 light years. I would like to know how thick it is. It is pretty dumb, but we'll talk about that. So, how high is the cake? Is what Andre is asking. Do you want me to ask all the questions at once, or are we doing one at a time?
Let's do them one at a time. That one's
Okay, so.
well studied, and indeed some of the work I did when I was kind of more active in this stuff than I am now was about that, about the thickness of the galactic disk. And colleagues of mine in the Galar survey.
Oh, I remember that.
Yeah, Galar was the Galactic Archaeology with Hermes being an instrument on the Anglo-Australian telescope. So some of my colleagues, and I'm thinking in particular of Rosie Wise and Jerry Gilmore, colleagues of mine in Baltimore and Cambridge, respectively, people I've known for a long, long time. They're not as old as me, though, but they're not, well, yeah, a similar generation.
They're not 26.7 million years old, billion years old.
Yeah, and a younger colleague who's probably only in his late 60s now, he might be younger than that even, Neil Reed, also in Baltimore. They looked at exactly this and came to the conclusion, which I think is accepted among the galactic astronomers. By that I mean people who study the galaxy, that our galaxy, our Milky Way galaxy, has two disks, which are called the thin disk and the thick disk.
That's right.
And the thin disk is the main one. That's the most dense one. And I I'm pulling numbers out of the air now here, but remembering back, of order a few hundred light years thick, so relatively thin for something that's 100 or 150,000 light years in diameter. But the thick disk its thickness is in thousands of light years. It's probably of order 1,000 or thereabouts light years. And so there are two definite populations. I think, if I remember rightly, too, the thick disk has an older population of stars than the thin disk. It's got more vertical motion within it, which is kind of what you'd expect because that's how it got thick. And it's much less dense. So the thick disk has fewer stars in it than the thin disk. So that's the bottom line, Andre. You might check on the web for thin disk and thick disk, and it should take you straight to this research.
Yes. Andre's second question, I would like to know if the plane of our own solar system is aligned with or tilted in comparison to the centre of our galaxy.
It's highly tilted, something like of order 60 degrees, maybe even more. And that's why, excuse me, when you think about the night sky, think about where the planets appear. They lie along the ecliptic. That's the plane of the solar system. And sometimes, when we see these lovely planetary alignments in the morning or evening sky, you see them strung out on a line. It's an obvious line. And that line goes right round the sky. It's tilted slightly to the line of the Earth's equator. Excuse me, not slightly. It's tilted at 23.5 degrees to the line of the Earth's equator because that's how the Earth rotates. But the ecliptic plane is the plane of the solar system. And then think of the Milky Way, and it's at a steep angle to the ecliptic plane. In fact, it's probably more than 60. That 60 is probably its tilt to the equator rather than the ecliptic. But it's a steep angle. It's almost, from if you were sitting with looking at the plane of the solar system as your as your plane, your reference plane, then the Milky Way is highly tilted to it. So what it's saying is that in fact, it's the other way around, of course. If you think of the plane of the Milky Way, it means the solar system is well tilted compared with that.
We're way out of kilter. And he wants to know, finally, is this the same for other solar systems in our galaxy?
People have looked at that, looking for any kind of common theme, where maybe all solar systems in our neighborhood are tilted at the same angle. The trouble is, with our current way of detecting planets, it's not that easy to work out the tilt of a solar system. There is a mechanism which has a double-barreled name, and I can never remember it, that does let you cleverly work out the tilt of the orbit of an exoplanet around its star. But it needs very fine measurements, really sensitive velocity measurements in order to do that. And so the sample of solar systems whose tilt we know is very limited, even though we know about more than 4,000 planets around other stars. We don't know much about them as solar systems generally.
Yeah.
So it's a relatively small number. And so I think the jury's still out on that. Although I think the evidence so far seems to be that there isn't any preferred tilt that you might.
So I know the answer. It's, wait for it, it's maybe.
Oh, maybe. That could be the answer. Yes.
That's the answer.
Yeah.
Yeah. All right. Thank you, Andre. Lovely to hear from you. And finally, Tom in Canada. Hello, Fred and Andrew. I'm a subscriber. Thank you, Tom. That's very generous of you and greatly appreciated.
Yeah, very much.
He said, and an admirer of your podcast since about episode 70. That was only a couple of weeks ago. I have two questions for Professor Watson. Your Wikipedia page mentions a few musical compositions you were part of. How does the cosmos inspire your music, and does music inspire any thoughts or ideas you might have in your astronomical research?
They're great questions, Tom. And my, I don't know. I never look at that Wikipedia entry because somebody wrote that years ago, and it's hugely out of date. But there's two parts to my musical life, and it's a very important aspect of my life. So my first love has always been, I know it sounds daft, classical music. I can still remember being among a bunch of young teenagers when I was probably about 11, and they were all hanging out, and they said, "So, what's your favourite tune?"
It was a Beethoven dance party. That's what it was.
No, it wasn't actually. They went round saying, what their favourite song was, and it was one said, "Rock Around the Clock," Bill Haley.
Oh yeah.
Don't You Rock Me Daddy-O. That was another one. And they went round, they got to me, and I said Ravel's Bolero. And they thought, who is this?
Who the hell is this guy?
And look, that's just been an interest throughout. So there is, I do work with a contemporary Australian composer by the name of Ross Edwards. He's very well known.
Yes, he is.
Classical music circles. And he and I have collaborated on a number of his works. I don't write the music because I don't have that skill. I write the words. And in fact, one of them won, you might be able to see it. In fact, I can point it out. That blue thing on the wall there.
Oh, yeah.
Is the 2008 APRA Award for the Best Choral Work, APRA Classical Music Award.
And APRA stands for Australian Performing Rights Association, just in case
right, yeah.
Not sure.
Right.
But that's, yeah.
I think I might be the only astronomer with an APRA Classical Music
How about
Award.
that?
But the other half, of course, is when I was at uni, I picked up a guitar. Somebody gave me a guitar and said, learn to play this. We were doing gospel songs, actually, at the time. That was what it was all about. And he said, we need somebody who can play the guitar. So he gave me the guitar. And by the end of the summer vacation, when I got back, I was better than him. Because I just took to it like a duck to water. And actually, on the other side, that case there, next to the bookcase, is it's a hard case that I occasionally use. It's a Hiscox case.
All right. Wait for it.
Oh, look, here we go.
Oh, you can't see it over there.
Oh, yeah. I can see something that might be a guitar. Oh, I see the guitar, yeah.
There it is. There it is.
It's cut away.
That's mine.
Very nice. Well, mine's got a Gibson Blue Ridge Custom in it that was made in 1968 and is something I've been playing for a long time. And so I got caught up in the folk blues world in the late 1960s, early 70s. I played with a lot of people who later became very big names. And still do a little bit. I sing Daft Science songs occasionally now at Science in the Pub. So it's not so much. I guess the music does inspire me in some way. I mean, there's bits of Sibelius, for example, that just speak of a shimmering night sky. It's just fantastic, and that cheers me up no end. But with the stuff with the guitar, the folky stuff, what I'm doing is trying to use it as an outreach tool to sing about the universe and hope other people will find that inspiring and interesting. With such songs as the Galaxy Redshift Blues and that big hit, The Universe is Like a Brick.
Oh dear. Tom, I hope you're glad you asked. You asked the question. He does have a serious question, though. Could black holes be safely used in gravity assist? I think someone else asked that recently. And what was the answer? No.
I think it's no. I mean, there is a serious side to that because, there are stars in orbit around the galactic center's supermassive black hole. One of them, I think it's called S4. There might be another one that's even nearer now. There's one of them that came within literally a few trillion kilometers of the black hole. It's in orbit with a period, I think, of about 12 years, if I remember rightly. But you won't want to get much nearer than that because then you start feeling the tidal effects. If your spacecraft is of any size whatsoever, one side of it will feel more gravity than the other, and that doesn't have a happy ending.
And everybody on the other side of the ship gets older faster.
Yeah, well, there's that too. Yes, you've got that as well as being spaghettified. It's just it's a no-win situation. And I don't think the answer to that is, I don't think it's maybe. I think the answer is don't go there. Don't go there
at all. No. All right. Thank you, Tom. Thank you, Andre. Thank you, Clive, for your questions. And a reminder, if you have questions for us, go to our website, click on the AMA tab, and it will give you the opportunity to send text or audio questions. Or if you want to stay on the homepage, just there's a tab on the right-hand side that's a very icky kind of green spearmint colour. Send us your voice message is another way of sending through questions to us or just comments. Just don't forget to tell us who you are and where you're from. And while you're on our website, don't forget to visit the shop, all sorts of doodads in there. And as Tom said, he's a patron. And if you're interested in becoming a patron, you can click on the Support Space Nuts tab and have a look at what that's all about. It's certainly not mandatory. It's totally optional and totally up to you and totally voluntary, which is three ways of saying the same thing, which is very astronomical to do. Fred, we are done for another day. Thank you, sir.
Pleasure, Andrew. Great stuff. What a thrilling! This could be a milestone, if in 10 years' time we're talking about a universe that's getting on for 30 billion years old. So we're seeing a watershed moment, a game changer.
Indeed, yes. And I dare say we will get, as I said before, a lot of feedback from the audience about that one. It might become as popular as talking about black holes and dark matter. Who knows?
Who knows?
Thanks, Fred. We'll catch you next time.
Sounds great. Thanks, Andrew.
Fred Watson, astronomer at large, joining us every week on Space Nuts. And being a Sunday, we let Hugh have a sleep in, although that's something he does 7 days a week, so nothing different. And from me, Andrew Dunkley, thanks for your company, and we look forward to chatting again very, very soon on the next episode of Space Nuts. See you then. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.